When I first heard about this card trick, I thought it was impossible. The spectator chooses a card, then by looking at 4 random cards, the magician correctly guesses the chosen card. Let me describe it in more detail. There are 3 people involved. You're the magician, I'm an assistant, and there's a spectator watching us perform the trick. The first step of the trick is that you actually leave the room. Then the spectator draws 5 random cards from a standard deck of 52 cards and chooses one of them. I place the chosen card face down and the remaining 4 cards face up. Then you enter the room, look at the face-up cards, and correctly guess the chosen card. Like I said, I initially thought this trick was impossible, so let me repeat it with an example. Again, you are the magician and you leave the room. The spectator draws 5 cards and chooses one of them. Let's assume it's the Jack of Clubs. I place the Jack of Clubs face down, and I place the other 4 cards face up. You enter the room, look at the cards, and correctly guess that the card that's face down is the Jack of Clubs. Before I explain how that trick is done, let's first consider a simpler version. This version still starts with you, the magician, leaving the room. The spectator draws 5 random cards, but instead of the spectator choosing one of them, I choose one of them. Like before, I place the chosen card face down and the remaining 4 cards face up. Then you enter the room and correctly guess the chosen card. This version is simpler because I'm your assistant, so I get to choose a card that's easier for me to communicate to you. But what exactly does this mean? Let's look at the same set of 5 cards from before. If I get to choose a card to communicate, which card do you think I'd choose? Try to see what some of these cards have in common. The answer is that I choose the 9 of diamonds. Let's see why. Like I said earlier, the reason I choose the 9 of diamonds is because it's easier to communicate than the other 4. How exactly do I communicate the 9 of diamonds to you? Here we get to the main idea behind the trick. The order of the remaining 4 cards is crucial. So let me rearrange the cards into this order. Notice which card is first. Maybe you can see where this is going. Before the show, we established a secret communication protocol. When you look at the 4 cards that are face up, the first card will always indicate the suit. In this case, you see the 5 of diamonds, so you know that the face down card is a diamond. The other 3 cards will indicate how much you should add to the first card. This step is trickier than just looking at the suit, but later, we'll see why these 3 cards in this order represents +4. Putting this together, you know it's a diamond and you know it's 5 plus 4, so you know that the face down card is the 9 of diamonds. Let's focus on the first step first. The first card indicates the suit. How come I, when I'm choosing the card to be set face down, can always ensure this? I can always ensure this because the spectator hands me 5 cards and there are only 4 suits, so some suit must appear twice. Okay, but why did I pick the 9 of diamonds rather than the 5 of diamonds? The answer here is that the 5 can reach the 9 by adding a number from 1 to 6, but not the other way. If we consider the ace as 1, jack as 11, queen as 12, and king as 13, then from 5 I can reach 9 by adding 4. Similarly, from 8 I can reach king by adding 5. We might have to wrap around from king to 1. For example, from jack I can reach 3 by adding 5. Note that 9 cannot reach 5 because even if we add 6, we would only get 2, which is less than 5. By the way, the property that ensures that some suit appears twice is known as the pigeonhole principle, and the reachability property is related to modular arithmetic. Both of these concepts are extremely important in a subject known as discrete mathematics. Okay, so now we know that the first card can always handle the suit because I'll pick a suit that appears twice among the 5 random cards. But what about the value? This is where it's important that the first card in the remaining 4 can reach the face down card by adding a number from 1 to 6. The remaining 3 cards will always indicate which of the 6 numbers you should add. In this case, let's see why these 3 cards tell you to add 4. First, we can label the 3 cards according to the following order: ace to king of clubs, ace to king of diamonds, ace to king of hearts, and ace to king of spades. So the ace of clubs is the smallest card, and the king of spades is the largest card. Note that any order will do, but this order is the one that I find easiest to remember because the suits are in alphabetical order. Anyway, according to this order, the smallest card is the jack of clubs, the middle card is the queen of hearts, and the largest card is the 2 of spades. So when I put these cards face up, I ordered them as 2, 3, 1 because it goes middle, largest, smallest. Notice that there are 6 ways to order any 3 cards, and this is how I communicate which number from 1 to 6 to add to the 5 of diamonds. If the order is 1, 2, 3, then you should add 1. If it's 1, 3, 2, then you should add 2. This pattern continues, and we can see that 2, 3, 1 corresponds to adding 4. But how do you memorize this chart? Well, 123 is the smallest number you can make using the numbers 1, 2, and 3, so 1, 2, 3 corresponds to plus 1. Similarly, 321 is the largest number you can make, so it corresponds to plus 6. This is how you're going to remember which order corresponds to which number to add. In general, the number of ways to order n items is n factorial, which is defined as n times n minus 1 times n minus 2, all the way down to 1. In mathematics, these orderings are known as permutations, and they are a key concept in a field known as combinatorics. In our case, we're ordering 3 cards, so n equals 3, and 3 factorial is equal to 6. So the order of these 3 cards indicates which one of 6 possible values to add to the very first face-up card. So let's summarize how I communicate the 9 of diamonds to you. The first card always indicates the suit, which is diamonds in this case. The order of the remaining 3 cards indicates how much to add to the first card to get the value of the face-down card. In this case, the order is 2, 3, 1, which is the 4th largest order out of the 6 possible orders, so the number to add is 4. So when you are seeing these cards, you should add 4 to the 5 of diamonds, and you know that the chosen card is the 9 of diamonds. What about the original version? In the original version of the trick, the spectator gets to choose which one of the 5 random cards gets placed face down. In fact, although the previous trick is already quite impressive, a keen spectator may notice that the face-down card and the first face-up card have the same suit. Once they notice that, then the illusion is halfway broken. So let's solve the original version now, where the spectator gets to choose the face-down card. Let's say the spectator chooses the Jack of Clubs. My job is to use the other 4 cards to communicate to you that the face-down card is the Jack of Clubs. How do I do this? Again, the order of the remaining cards is crucial, so let's rearrange them like this. For this version of the trick, we'll be using a different communication protocol, but the logic will be similar as the earlier version. Recall that last time, the first card tells you the suit, and the other 3 cards tell you a number from 1 to 6. This time, all 4 cards will work together to tell you a number from 1 to 24. Then there will be an extra signal that indicates whether or not you should add 24 to the number from step 1. This allows me to communicate one of 48 possible numbers to you. Since there are 48 cards that you cannot see, you know which card I'm trying to communicate. Let's work through some examples. The first part of the protocol is that the order of the cards indicates a number from 1 to 24. Again, there are 48 cards remaining, but let's not worry about that for now. We can order the remaining 48 cards as we did earlier, starting with the Ace of Clubs at number 1 and ending with the King of Spades at number 48. The Ace of Diamonds is number 14 because there are 13 cards that come before it, but things can get a bit tricky. The 6 of Diamonds is typically 5 cards after the Ace of Diamonds, so we'd usually think it's 19. But it's actually 18 because the 5 of Diamonds is one of the face-up cards. This is also why the last card, the King of Spades, is number 48, even though in a full deck of cards it would be number 52. Anyway, since you and I can both see the 4 cards that are face up, we can both mentally label each of the remaining cards with a number from 1 to 48. Now, instead of communicating a card to you, I'm communicating a number from 1 to 48. To do this, we do something similar to part 2 of the previous protocol, but now we have 4 cards instead of 3. Since you see 4 cards, there are 4 factorial, which is equal to 24 possible permutations. The permutations that start with 1 correspond to numbers 1 to 6, the permutations that start with 2 correspond to 7 to 12, the permutations that start with 3 correspond to 13 to 18, and the permutations that start with 4 correspond to 19 to 24. Notice that within any column we have 6 permutations, so this is basically the previous protocol, but augmented by a factor of 4. When you look at the 4 face-up cards, you can label them again just like last time. The smallest card is the 5 of diamonds, so that gets a 1. The next smallest is the 9 of diamonds, which is 2. then the Queen of Hearts is 3, and the largest card is the 2 of Spades, so that's 4. So overall, the order of cards that I'm showing you is 2, 4, 1, 3, which corresponds to 11. Now you know that the number I'm trying to communicate is 11, which means the face-down card is the 11th card out of the remaining 48. The 11th card is pretty easy to determine because it's in the first suit and there aren't any clubs that are facing up. Of the remaining 48 cards, number 11 is the Jack of Clubs, which is what the spectator chose. Remember that if there were any clubs on the table, then you'd have to adjust accordingly because those cards aren't counted in the remaining 48. But now the question is, what about cards 25 to 48? For example, what if the spectator chose the 8 of Spades, which appears much later in the deck than the Jack of Clubs? This is where the second part of our communication protocol comes in. An extra signal from me indicates if you should add 24 to the number you got from part 1. Among the 48 cards, the 8 of Spades is number 43. How did I get this? Well, the King of Spades is 48, and 8 is 5 below King, and 5 below 48 is 43. To communicate 43 to you, I split 43 into 19 plus 24. I then communicate 19 using the previous protocol, which means I'll show you the order 4, 1, 2, 3. Then I'll do an extra signal that indicates plus 24. By seeing the 19, as well as the extra signal, you'll know that you should add 24 to 19 to get 43, and then you'll know that the face-down card is the 8 of Spades. Let's see this in action. To communicate 19, I need to order the cards as 4, 1, 2, 3. This means I put the largest card first, and that's the 2 of Spades. The remaining cards just go in increasing order 1, 2, 3. So that's the 19 part, but what is this extra signal that I've been talking about? For this part of the trick, we won't be using any math. Instead, there are a number of sneaky ideas we can use. These ideas are much more common in non-mathematical magic. For example, one possible signal is using a secret word. I might tell you to predict rather than guess what the face-down card is. Or I can do something simpler like faking a cough. In my opinion, a cleaner idea for the extra signal is a visual one. When I'm displaying the cards on the table, I can either spread them out like you currently see them, or I can overlap them like this. If I overlap them, then that means you should add 24 to the number from part 1. Or you and your assistant can decide that spreading the cards out means to add 24. This part of the trick has a lot of flexibility. With different ways of overlapping or different secret words, I can communicate even more information to you. But for the purposes of this trick, you only need to know whether or not you should add 24, so a yes or no signal, also known as a binary signal, is enough. Let's review the simpler version of this trick. You leave and the spectator draws 5 random cards. I'll look for a suit that appears twice, and in that suit I'll choose a card that can be reached by another card in that suit. Remember that being reachable means that I can add 1 to 6 to the non-chosen card to obtain the chosen card. I'll put the lower card first, which tells you the suit. Remember that lower could mean, for example, Jack, and I want you to add 5 to get to the 3. Finally, there are 6 ways to order the remaining 3 cards, and their order indicates how much to add to the lower card. Let's do a quick example. Let's say the spectator draws the 2 of clubs, the 4 of clubs, the ace of diamonds, the 5 of hearts, and the 5 of spades. A suit that appears twice is the clubs. I'll choose the 4 of clubs and put the 2 of clubs first. The remaining cards are ordered as ace of diamonds, 5 of spades, and 5 of hearts. This permutation is 1, 3, 2, which corresponds to plus 2, so you should add 2 to the 2 of clubs and know that the chosen card is the 4 of clubs. There are 2 parts of this trick that are pretty neat because they just barely work. For one, the way I communicate the suit wouldn't work if the spectator only drew 4 cards, because there might not be a suit that appears twice. Also, the reachability part wouldn't work if the deck has 14 rather than 13 cards per suit. For example, if there are 14 cards in a suit, then 1 cannot reach 8, and 8 cannot reach 1. Finally, let's review the original version of this trick. You leave, the spectator draws 5 random cards, and the spectator chooses one of them. Once you see the 4 face-up cards, you'll know that there are 48 possibilities for the face-down card, so let's let X denote its order. I'm trying to communicate x to you, and I can order the remaining 4 cards in 4 factorial, which is 24 different ways. If x is greater than 24, I'll do an extra signal, such as a secret word, in order to indicate that you should add 24. Let's do the same 5-card example as before, but this time suppose the spectator chose the ace of diamonds. In a full deck of 52 cards, the ace of diamonds would be number 14. But since there are 2 face-up cards that come before it, it's actually number 12. To communicate 12, the correct order is 2, 4, 3, 1, and there's no need to add 24. Finally, once you know that x is 12, you can reverse the thought process to conclude that the selected card was the ace of diamonds. Again, a neat thing about this trick is that it also just barely works. If the deck had 53 cards, then there are 49 possibilities for the face-down card, so this communication protocol wouldn't always work because it can only communicate 48 numbers. The simpler version of this trick is attributed to Fitch Cheney, and the original version is attributed to Martin Gardner. For more information about this trick and many other tricks, there's actually an entire book written by Colm Mulcahy called Mathematical Card Magic. If you like this video, I recommend that you check out the book.